Ammonia is a weak base and is still a key ingredient in some glass cleaners, though it's less common now as gentler alternatives become available. For this example, let's set up a slightly strange scenario. Let's say that I need to determine the concentration of an ammonia-based window cleaner to at least the millimolar level, so 3 decimal places. Ammonia is a weak base, so I can titrate it with a strong acid until I reach the equivalence point, and use that to determine the original concentration of the ammonia in solution. However, let's complicate things by saying that I have a high-quality 1.000 molar solution of sodium hydroxide, or a strong base, but my strong acid solution of HCl is much less reliable, maybe only known to a single significant figure. The volumetric equipment is also a source of error, but let's just say that I have a very precise and recently calibrated system that can measure accurate to the microliter, so the error introduced from those measurements is so much lower than the concentrations that we can basically ignore it. Since we need to use the strong acid solution, the HCl solution, on the ammonia, we can start by titrating a sample of it with the NaOH solution to determine its concentration to much higher precision than we have right now. The equivalence point for a strong acid, strong base solution is always pH 7, so we can see how much of our 1.000 molar sodium hydroxide solution we need in order to reach pH 7. After running the test, we find that it took 11.620 milliliters of our 1.000 molar NaOH solution to neutralize a 10.000 milliliter sample of the acid solution. That means that the moles of hydroxide in the high precision solution are equal to the moles of the acid, or the hydronium, in the unknown sample. 11.620 milliliters times 1 liter per 1,000 milliliters times 1.000 moles per liter gives us 0.01162 moles of hydrochloric acid in 10.000 milliliters, telling us that the concentration of HCl in our strong acid solution is 0.01162 divided by 0.01 liters, giving us a 1.162 molar solution. And now that we have the concentration of the strong acid solution at a much higher precision, we can use it as a standard against which we determine the concentration of ammonia in the window cleaner. To do that, we'll take 10.000 milliliters of the window cleaner as a test sample and slowly add the HCl solution. The strong acid reacts with the weak base to produce NH4+, ammonium, ammonia's conjugate acid. This creates a buffer solution, and until we get close to the equivalence point, the buffer region is going to slow down the change in pH per additional drop of strong acid. Eventually, though, we add more moles of HCl than there were of ammonia in the first place. The additional hydronium ions have no base to react with, and so the solution pH drops quickly. That's our equivalence point. Adding more acid past this point will continue to gradually drop the pH, but it isn't telling us anything new. So if we find that it takes 25.340 milliliters of our 1.162 molar HCl solution to reach the equivalence point in our 10.000 milliliter ammonia sample, then that means that it took 25.430 milliliters times 1 liter per 1,000 milliliters times the concentration 1.162 moles per liter, giving us 0.02945 moles of HCl needed to react with every ammonia molecule in the original solution, telling us that there were 0.02945 moles of ammonia in 10.000 milliliters. And so by knowing that, we can find the concentration is 0.02945 moles divided by 0.01 liters gives us a concentration of 2.945 molar of ammonia in the glass cleaner. At this point, we can add some more data to our plot. For one, we can find the half equivalence pH at 9.25, and since Henderson-Hasselbalch tells us that the half equivalence is equal to the pKa, We know now that the pKa is 9.25, meaning that the Ka value is 10 to the negative 9.25, or 5.623 times 10 to the negative 10. The pH at the equivalence point depends on the dissociation of the conjugate acid, and we can use an ice table and equilibrium expression to see that 5.623 times 10 to the negative 10 equals x squared over 2.945 minus x. Now that dissociation constant is so small that we really expect this x to be negligible compared to the 2.945. And when we calculate for x, we find that it's 4.069 times 10 to the negative 5. That's the concentration of hydronium at the equivalence point, so pH at the equivalence point is 4.39. And now that we know the concentration of ammonia in the window cleaner, we can use the same method to find the pH at any point on the plot, or we can use Henderson-Hasselbalch in the buffer region. If, for example, we still want a high concentration of ammonia in order for a good cleaning effect, but need to moderate the pH in order to protect the window frame, we now have all the tools we need to find the right solution for the right application.